So this is a joint tutorial between myself and Robin Evans. So in the first part, I'll be describing results on non-parametric identification of intervention distributions. And essentially, the key idea is we'll suppose that there's some underlying causal DAG of latent variables, and our goal will be to come up with expressions that identify intervention distributions. The second part will be Rob will present that, and it will be more statistical in flavor, in that it will be talking about sets of distributions that are defined by constraints that arise from DAGs with latents. So in some sense, part one, you can think of, we will be doing operations essentially on one distribution. Part two, we'll be talking about sets of distributions. So this is the outline for part one. I'll start off talking about an intervention distribution, and then that will lead into the general identification problem that arises when not all variables are observed. And then I'll present an algorithm that solves that problem that's due to Tian, the ID algorithm. I'll present it in a slightly novel way, but the basic ideas are all in Tian's papers. And then I'll briefly talk about how these methods also give rise to non-parametric constraints that generalize conditional independence, and that will sort of set the stage for Rob's part of the talk. So our basic idea here is we're going to have a causal DAG. It's going to, or Bayesian network, we can think of as just represent a joint distribution over a set of variables in a way that I'm sure is familiar to almost everybody here, I hope. But we're now going to be computing an intervention distribution via a truncated factorization. So when we intervene on a set of variables x, we just delete those variables from our factorization. We delete those terms from our factorization, and we set the variables that are intervened on set for the specific values. So for example, if this is our graph here, then the joint distribution is as follows, factoring into terms for each variable given its parents. And now, if we're interested in intervening on x, then we're then going to cut out this term from our factorization. And if we're setting x to the value of x tilde, then here, instead of having n given x, it's now going to be n given x tilde. So this now represents a distribution over L, M, and Y, and we have one for every value of x that we might want to increase. Okay. So it might be that we don't actually care about the intervention distribution on all three variables. We might only be interested in the intervention distribution on y. And so if that's the case, then we can just sum out the variables that we don't care about. And so we end up with this general expression, which identifies the effect of x on y. X and y can be sets here potentially, in the context of a DAG where all of the variables are observed. This in fact predates the notion of a DAG. It's an instance of the G computation formula of Robbins. And one thing I want you to notice here is the form of this general expression, that it's a product of terms of the form B given the parents of B, and then the sum over that product. And we're going to, because the solution we're going to have to the harder problem with latent variables will have a similar form to that. Okay, so for example, if we consider this case here, which we looked at before, if I'm now only interested in the distribution on y when I intervene on x, then I just take the expression I had before, but now I sum out L and M. And the key point here that the reason why we're writing do x equals x tilde here is that this is not the same thing as just the ordinary conditional distribution for y given x equals x tilde. And if you want to sort of convince yourself of that quickly, if it's not immediately obvious, if we think about the case where, say, this edge from M to Y is not present. So if we get rid of that edge, so then here, if this is our observable distribution before we do our intervention, and we then look at the distribution when we intervene on X, we then get this graph over here. And then if we were to sum out L and M, then simple algebra shows we can sum out M. We then get to this expression, which then lets us sum out L. And then we then find, as we would expect, that the distribution over Y when we intervene on X in this graph is just the marginal for Y. But that is not the same thing as the conditional distribution for Y given X, because we can see just by this deconnecting path that Y and X are not independent. So we can see the difference between conditioning and intervening. Okay, so now let's consider the case where M is unobserved. So if we didn't observe M here, then we could still take the expression that we had, that we could derive from this DAG. But if we hadn't observed M, then obviously we wouldn't have these conditional densities to hand. But we can use the independence that's present in the original graph. So we can see, for example, that M and L are independent conditional on X. So we can add in L here. And we can also see that Y, in this graph here, we can see that Y is independent of X given L and M. So we can add in X here and we can add in L here. And then a little bit more rearrangement, we can then combine these two terms to get Y and M given L and X. And we can then sum out M from this. And we get this expression here, which now no longer involves M. So that even if M was not observed, we can see that we can get the intervention distribution here. We can get the effect of X on Y, even if we didn't observe M. And this is the formula we've got here is an instance of the backdoor formula. The idea being that L is on the backdoor path between X and Y. Okay, what about if L was unobserved? So if we didn't observe L, then we can take a slightly different approach, and we can say, well, suppose that I could get the effect of X on M, and that I could also identify the effect of M on Y. Well, then I could multiply those two things together, and then sum over M, and that would then give me the effect of X on Y. And if we look at this, well, the first piece, the effect of X on M, if we looked at this, we could say, well, suppose that, I could just imagine marginalizing over both L and Y, and then I'd just end up with this graph with just X and M. It's pretty simple. If I applied that's just a DAG with no hidden variables. If I applied the intervention formula to that, I could convince myself that M given do X is just M given X. So now the only piece I've got to do is this other piece over here, Y given do M. But now if I look at that, I can see that's similar to the backdoor formula. So if I look at this, here I've got M, I want the effect of M on Y, and now I've got this backdoor path, but X is sufficient to block that backdoor path. So I can use the backdoor formula here to get the effect of M on Y. And so it shows that even if L is not observed, I can still identify the effect of X on Y. So this is an example of what I'll call the front door formula. So far so good. We've seen if we don't observe M, we can still get the effect of X on Y. If we don't observe L, we can get the effect of X on Y. But obviously, not every story is going to have a happy ending. If we don't observe either L or M, then we're out of luck, because I'm just giving you a joint distribution over X and Y, and clearly we can imagine at least two possibilities. One being that X has no effect on Y, and the dependence is entirely due to confounding, the other being that there's no confounding. This is what's going on. So clearly, not every time we ask if something is identified in the context of a DAG with hidden variables, will we be able to be able to come up with an identifying formula. So here's the general identification question that I'm going to consider in the rest of this talk. So I'm going to start off with a DAG with observed and hidden variables, and then the question we're going to ask is if I take two subsets, X and Y, subsets of the observed variables, is that intervention distribution identified from the distribution over the observables. And we either want to provide an identifying formula that's a function of the distribution over the observables, or report that it's not identified. Okay. I'm going to introduce a little bit of carrying around these models with hidden variables. That they can get a little cumbersome. And so I'm going to present some notation for that allows us to write graphs with, to simplify graphs that include hidden variables. And so I'm going to do that by using what's called the latent projection, which is a fairly simple idea. The idea is that I want to take my graph that's got my DAG with latent variables and transform it into a graph where I have directed and bidirected edges. And the idea is that if I have a path from x to y that's a directed path and everything on that path is a latent variable, then I'm going to put in a direct edge from x to y. And if I have a path between x and y starting from some latent common cause, so there's some latent common cause with a directed path from there to y and from there to x, then I'll get rid of these latents and replace, put in a bidirected edge between x and y like this. And then we'll remove all the latent variables from the graph. Okay, so for example, if this is my DAG here, then I've got two latent variables here, u and w, and then when I do the projection, so I'll end up with a directed edge from y to t due to this path, directed edge from z to t due to this path, and also I've already got a directed edge here. And then I'll end up with bidirected edges between x and y and z, and x and z. And so this leads to a graph. The new graph that I'm going to construct will not have any directed cycles, and so we can call it an acyclic directed mixed graph. So that it's mixed because it contains directed and bidirected edges, and it's acyclic because it doesn't have directed paths. So, okay, go ahead.
Suppose u did not exist.
Yeah.
Would there still be a bidirected edge between z and y because of the W, the collider?
No.
Okay, so latent colliders don't produce edges.
Yeah.
Okay.
The question is like, what if you have a latent and a direct path? Then the graph won't be simple, right? I mean, are you going to have both edges?
Yeah, you could have both edges. Yes, you could have a directed and a bidirected. So your question is if I had if I had this where this is latent, then in that case I'll end up with a graph. Okay. So it's not necessarily simple. I mean, it doesn't necessarily have just one edge between their vertices. Okay, we can read off the independencies by just the usual rule. If you're familiar with these separations, we just... Another question.
This graph wouldn't distinguish if there were three separate u's.
No.
Three independent u's between x and z, z and y and x. Why does that not matter?
That's another talk.
Robin will discuss that towards the end of his talk. But basically, for the purposes of identification, it's not going to matter. It matters if you get very interested in things like inequalities, but it's not going to matter for identification or equality constraints.
Do you have a quick intuition?
I defer that to Rob, the expert on this. But,
I don't have a quick proof, but for the purposes of this talk, you could just consider a clique of bidirected edges to mean a single latent variable, not pairwise one.
other questions? So we can read off independencies by using deseparation, random separation. Just the idea that if I have two arrowheads, that's a collider on a path. If I have two arrowheads, it's a collider, and the notion of ancestor and or descendant is the same. So just deseparation applies directly. Okay, so we've already seen these graphs. We had these graphs where we had intervened on certain variables. And so just to sort of formalize that notion, we're going to have this graph that, for historical reasons, called conditional acyclic directly mixed graphs. But the basic idea is we're just going to have some variables that have been fixed or intervened on. You could think of that if we're going to represent as being square. So these are just graphs that represent a set of distributions over the variables in circles that we'll say are in V, indexed by the variables that are fixed, that are squares. And the only edges that are allowed between the fixed ones and the variables in W, the fixed and the random vertices, are all directed from the fixed vertices to the random ones, and there are no edges between the fixed vertices, because this is representing a distribution over V indexed by the variables in W. So you can specify a set of values for variables in W and get a distribution over V. Okay, so here, for example, W, the fixed guys are A0 and A1, and the random guys are L1 and Y. And the notion of ancestor and descendant is exactly the same as it was before. So in this example here, the ancestors of Y are A0, L1, and A1. So now another notion, we've got bidirected edges, so we have an idea of a district. And so a district is just a maximal set that's connected by bidirected edges. So in this example here, there are three. I don't know if you can see this. If you look over there, you can see it. But, we have three districts. So 1 and 2 forms a district, 3 and 4 forms a district, and 5 forms a district. So, and districts arise very naturally because if I go back to thinking about this as a DAG with latents, as we had over here there on the right, and then we think about marginalizing out the latents. So this is just the usual DAG factorization, and then marginalizing out U and V. And if we push in the sums over the latents, we find that we end up with these sort of conglomerations of terms that involve vertices that are all in the same district. So we can.
If I turn bidirected edges into undirected, is it a chain graph?
So I'll come back with the next slide will address exactly that question. So just hold your horses on it. So basically here, the key point is when I push this in, this is a function of x1 and x2. This is a function of x3 and x4, conditional on x1 and x, or index by x1 and x2, and this is a function of 5 and 3. Okay. So we can factor into terms into distributions over these are not necessarily ordinary conditional distributions. But we can factor into distributions over a set of variables in a district, conditional on the parents of the district that are not in the district itself. So coming to, and these are also called. I should add these were also called C components in Tian's. So going to Milan's question, from this example, you might get lulled into a false sense of security by thinking that you could sort of think of the districts as being blocks with directed edges being, so put a total ordering on these blocks and then have directed edges between blocks consistent with that total ordering on the blocks. So whatever it is, red, green, blue, and then edges following in those directions. But in general, you're not able to do this. So if you have a graph like this, which we could easily draw the latent variable model that would give rise to this. Then here I've got, this is one district, this is the other district, but we can have a directed edge that goes from 1 to 3, and then a directed edge that goes from 4 to 2. So there's no ordering on the vertices. In general, there's no ordering, total ordering on the vertices, such that the parents of a district will precede every vertex in the district. And that makes working with these factorizations a little bit more complicated. So you can't in general form a chain graph. Okay, a little bit of notation for districts. So if I give you a vertex, we can then find the district that it's in, the districts partition that are around the vertices. So just by convention, things that are fixed like A0 are not in districts. So when we talk about district, it's a subset of the things that are in V. Okay, so only variables in V are in districts. So in this example here, the district for Y consists of Y, L0, and L1. The district for A1 just consists of A1 itself. And we'll write D of G to denote the set of districts in G. So that will always be a partition of the random variables in the graph. Okay, so let me now give you the overall high-level view of how we're going to go back to that identification question. So remember, I'm coming to you with a DAG of latent variables and a query: can I identify the effect of intervening on X on the set of variables in Y? And so we're going to attack that question in 2 steps. So the first step will be to show that we can re-express the query in the form sum over a product of terms where each term is going to be a district, given that we intervene on the parents of the district that are not in the district. Okay? So this formula is like a generalization of the formula that we saw in the case of a DAG without any hidden variables, in which case each one of these was just a singleton, it was just V given the parents of V. And the second thing will be that we will check for each term over here, we will check whether or not that intervention distribution is identified. And that's clearly sufficient for identifiability, because if I can show you that each one of these intervention distributions is identified, then clearly I've identified the formula on the left. But it turns out that this is also necessary, and that follows from the completeness proof due to Richardson. Okay, so I'm going to tell you first how to do step A, and then I'm going to tell you how to do step B. I'm going to have an explicit graphical way of doing each of these. So remember the first thing I'm doing. I'm telling you how to. You're going to come to me with a query like this, and I'm going to show you how to rewrite it in this form. So I'm first going to cut all the edges into X. So I'm going to start off with a DAG, and I'm going to say, suppose that we intervene on all the variables in X. So I'm just going to let this graph is just a notation for the graph where I intervene on everything in X. And then I'm going to say, I'm just going to throw out any variables that are not ancestors of Y. So I'm going to restrict the variables that are still ancestors of Y after I've intervened on variables in X. And then that gives me a subgraph of the graph that I formed at step 1. And then I just look at the districts of that. Okay, so there's 3 steps. First step was intervene on X. Second step was throw out everything that is not an ancestor of Y in the graph where I intervene on X. And the third step is then look at the districts that are in that resulting graph. So, and then the query that I'm interested in can then be written by taking a product of those districts, each one intervene on the parents of the district that are not in the district, and then summing over everything that is in DI but is not in X or Y. So summing everything that I care about. So here's a very simple example of the front door graph. So if I have this is the graph. My query is, can I get Y given do X? Of course, we know that we can, but let's just go through the steps as to how we do this. So I intervene on X. That gives me this graph over here. Now I restrict attention to the ancestors of Y. That's everything here. Every vertex here is an ancestor of Y. So I don't throw anything away. And then I look at what are the districts here. In the districts, I've got 2 districts, Y and M. Then tells me that, so using a result, I can then express Y given the intervention distribution for Y intervening on X as the sum over M given do X and Y given do M summed over M, which is the expression I showed you before when we were going through the steps of deriving the front door formula. So let's look at another graph. So this is a graph that arises. It's often called the Verma graph. or yeah, I guess sometimes that's the graph. Sometimes this edge is left out when it's called the Verma graph. But the basic, this graph arises in the context where A0 is a treatment, and then A1 is a second treatment, A0 is randomized, and A1 is also assigned randomly, but conditional on your observed history up to that point. So A0 is a treatment, so initially assigned L1 is a response to that treatment, A1 is then assigned randomly, but with probability depending on your observed history to that point, and then Y is the final outcome, and this red edge indicates that we think that the final outcome, that these two responses, the way you respond to the first treatment and the way you respond to the second treatment could be confounded by your underlying health status. So in this case, we want to see, can we identify the distribution over Y when I intervene on A0 and A1. So here, my first step, remember, is to intervene on the variables that I want to intervene on, which are A0 and A1. This gives me this graph. And then I restrict to the ancestors of Y, which in this case is just A0, A1, and Y. And then I look at the districts in that graph, which in this case is just one vertex. And the representation of the query is then trivial here because I don't have any summation or any product to do. So I just have Y given do X is equal to Y given do X. So Y given do A0, A1 is equal to Y given do A0. Okay, so that's the first step. So that I've shown you these three steps get us to this expression. It's a product over districts intervening on their parents, the sum over a product of districts intervening on their parents. So now, now we have to work out. Now I have to give you a way to find out if this is identified. So D is going to be a district in the graph, in this graph G star. And I have to work out whether or not this thing is identified. And so basically, it's going to be an inductive argument. What I'm going to do is I'm going to say, okay, let me find everything that is that's not in D. Let me see if I can find an ordering of everything that's not, all of the observed variables that are not in D, such that we have the following property, that if we'd already identified the distribution where I intervened on R1 to RT minus 1, if that was already identified, then the distribution where I also intervened on RT is also identified. So what I'm going to do is I'm going to give you an ordering of the other vertices, the vertices that are not in D, such that at each stage, if I've identified the intervention distribution where I intervene on R1 to RT minus 1, then I can also identify the distribution where I, in addition, intervene on RT. So this is obviously sufficient for identifiability because this distribution is identified, and if I can intervene on everything else, then I'll end up with this intervention distribution that I care about. Okay, so everyone clear on the game? The game is that I'm going to start off with the observed distribution and then sort of in sequence intervene on every variable that is not in the set D that I'm trying to get to. And I'm going to use a little bit of terminology. I'll say that RT is fixable if I can find a vertex RT that satisfies this property, so that given that I've already identified this, then I can also, in addition, intervene on RT and identify the second distribution, and I'll say that RT is fixable given that we've already fixed R1 to RT minus 1. And you might be saying, why are we introducing this term fixable? It sounds very much like it's synonym for do. What's the difference? The difference is that I can always talk about intervening on variables, but an intervention distribution may or may not be identified. When I'm fixing things, when I use that term fix, I'm guaranteeing to you that the distribution I'm constructing is identified. And it will have an interpretation under the latent variable model, it will have an interpretation as an intervention distribution. Okay, so I have to do two things to finish this off. I have to give you a graphical characterization of fixability, and I have to show you how to construct the identifying formula.
Question on the fixing doesn't do, is that the same difference as whether you're removing edges from the node in the graph versus making a square node?
So I think basically, so the point is you can always cut edges you can always remove edges from the graph. The question is whether or not the resulting distribution is identified. So in some sense, fixing is like a special case of do. Okay, so here's the key definition as to when something is fixable. A vertex will be fixable in a graph if it has no proper descendant that's in the same district that it's in. So another way of saying that is V is fixable if there's no other vertex y that can be reached both by a path on which every edge is bidirected and by another path on which every edge is directed. So if V doesn't have any descendant that's also in the same district as V, then V is fixable. So this will be the set of fixable vertices is a subset of V, and it contains at least one vertex from every district in G. So you can sort of see that if I'm in the district, if I'm at a vertex that's not fixable in the district, then that means it has a descendant in the district. So I go to that descendant, and then I just keep on doing that until eventually I get to some vertex in the district that has no descendant in that same district. Okay, so let's look at some examples. So here was this front door graph that we looked at. So here, the fixable vertices are M and Y. Well, why is that? Well, Y has no descendants at all, so it's obviously fixable. M has some descendants, but it has there's nothing else in the same district as M, so both M and Y are clearly fixable. X, on the other hand, is not fixable because Y is a descendant of X and Y is in the same district as X. Here's the Verma graph. So in this graph, Y, A1, and A0 are all fixable. Well, that's because A0 and A1 are easy because they're just their districts are just singletons. A0 is just its district just consists of itself. Likewise, A1. Then Y is Y has no descendants again, so it's also fixable. L1 is not fixable for the same reason that L1 has Y as a descendant and Y is in the same district as L1. Okay, so that's the notion of fixable. So now, I'm now going to describe to you an operation that will both be on a graph and on a distribution that will fix a fixable vertex. So what does that mean? What does it mean so the graphical operation is very easy. It's basically just replacing instead of R being in a circle, we'll put R in a square box and cut any bidirected edge, or any edge that has an arrowhead at R will be removed. So that's very easy. It's just like the do operation that we were doing before. So fixing R transfers R from V to W and removes any edges that have an arrowhead at R. So here, for example, with this front door graph, we saw that the set of fixable vertices was M and Y. If I choose to fix M, could have fixed Y, but if I choose to fix M, then I then get this graph. You can see M has gone from being a circle to being square, and I've got rid of this edge. Now notice something interesting here, which is that in the original graph, X was not fixable. But now after I fixed M, in this new graph, X becomes fixable. So we see that after I fixed M, I'm able to fix X, but before I fixed M, I can't fix X. So if we look at this Verma graph, it's similar. So I could fix A0, A1, or Y. If I choose to fix A1, then I then get this graph down here. A1 is now in a box, so I cut the edges into A1. And now, if if I think about what are the vertices that are fixable in this new graph, I see that, as in the previous example, L1 was not previously fixable, but it is now fixable. Marie?
And is it true in general that a node cannot become unfixable if it was fixable in the beginning?
Correct. Yes, that's also the case. That's yes, because we're removing edges. So given that the way that you're not fixable is because the existence of paths, since I'm removing edges, if you were fixable before, you're still fixable afterwards. Okay. So that's the graphical operation. We also want to have we're using these graphs to represent distributions. So we want to have a corresponding operation on distributions. And that operation is as follows. So I'm going to come to you with a distribution over V given W. This won't necessarily be a conditional distribution for the original join. I have some set of distributions over V indexed by W. And the operation that I'm going to do is I'm going to take that distribution and I'm going to divide by R is the thing which is fixable. I'm going to divide by R conditional on every other vertex that is in the district containing R, or that is a parent of a vertex in that district. So anything that's either a parent of R or is connected to R by a sequence of bidirected edges, or connected to R by a sequence of bidirected edges and a directed edge like this. So basically chaining out colliders. Okay, and it can be shown that if R is fixable in G, then as required, the new distribution that we obtain by doing this division corresponds to the distribution where I have intervened on R. So an interesting thing about this is this operation, dividing by this R given this set of vertices down here, corresponds to, in special cases, it corresponds to both marginalizing and what's sometimes called truncating and dividing by. And so this operation can be seen as crossing out the term from the DAG factorization. Think about it. In the simple case of a DAG, if this was not a graph of bidirected edges, if it was just a DAG, then when we would be dividing by R given the parents of R. So it would correspond to just crossing out the term from the DAG factorization. So the interesting thing is that that in this way we can roll into one kind of operation, both marginalizing and crossing out terms from a factorization. So in particular, if this set consists of everything except R, then fixing just corresponds to marginalizing. I'm just taking this, dividing by this, and I'm getting the resulting margin. In the other direction, the other extreme, if this set is just W, then the operation, then the resulting distribution that I get out is just like the distribution you get by ordinary conditioning on R starting off from V of V and W. So if you compute it, the distribution of V minus R conditional on W union R from this, you get that out. So this covers both marginalizing and conditioning, which sometimes in these identification algorithms there have been separate marginalizing steps and division steps, but those can be rolled together by this notion of fixing. In general, if it's not one of these extreme cases, then it corresponds to a reweighting, but we're going to get something which is neither an ordinary marginal nor an ordinary conditional. That's the reason why causal identification is more complicated. Okay, so we also saw earlier that we had situations where we're going to want to fix. We're going to want to fix one vertex and then fix another one later. And so we're going to compose this fixing operation in the obvious way. So if I first fix S and then I want to fix R, the graphical operation is just as you would imagine it. First fix S and then fix R on the graph. And the probabilistic notion is also the natural one you would imagine, that we're going to start off with this distribution, and then we're then going to construct a new distribution by fixing S in this distribution, and then we're then going to fix R in the resulting distribution. Okay, so here, let's look at the front door graph. So remember, when we did the front door graph, we wrote it in the form as a product, sum over product of terms with districts. We had two districts. One was M and one was Y. So let's first look at the one that just contains M. So we want to fix, this is what we're aiming for, M given 2x. So we want to fix Y and X. Up here, we're not able to fix X. We obviously can't fix M because we want M to not be, we want M to be around at the end. We never want to fix something that's in D. But so here the only thing that we can fix here that is not M is Y, so we then get to this graph, and then we can fix X, and we get to this. So this then shows, this sequence of operations shows that, that this distribution is identified. So the key point here is that we can do this greedily, because of the observation that Marina made, that we never lose fixability. I can just choose anything, any vertex that I can find that's fixable that's not in D, I'm able to fix it without worrying that I might have to backtrack and do things in a different order. This was the other graph, this was the other vertex we wanted to get from. We wanted to show that we could get a distribution of Y given 2M, and here we obviously can't fix Y because we want it to be around at the end. We can't fix X, so we have to fix M, this graph, and then we can fix X. So that we've shown that this is also identified. The Verma graph here, remember we just had one district which consisted of Y. So here we can first fix A1. We could also fix A0, but we could fix A1, that gets us to this graph. Then we can fix, in this graph we can fix either L1 or A0. Here we happen to fix L1, which gets us to this graph, then we can fix A0, and then we have shown that this is identified. Okay, so that's basically the algorithm. So now, just summarizing what we went through, we did two steps. One step was to re-express the query as a sum over a product of intervention distributions on districts in this way. And we found these districts by cutting the edges into X, restricting the vertices that remain, that are still ancestors of Y after we cut the edges into X, and then finding a set of districts in that resulting graph. And then for each one of those districts, we then via this fixability, find out whether or not, if we can fix everything that's not in DI, then indeed this is identified. If at some point we get stuck and there's nothing, there's no vertex that we can fix that is not in DI, then we conclude that this piece is not identified. So to sort of see a trivial example of this, suppose that I took this graph, the front door graph, but now adding something between X and M, and I said, okay, I would like to find the distribution of Y intervening on M. Well, in this graph now, I can't, M is no longer fixable, because Y is in the same district as M, and Y is a descendant of M, so Y is not fixable here. I also don't want to fix Y. So basically, I can't fix it. So I can't fix M, and I can't fix X in this graph, so I'm stuck. So if I'm trying to get to this, I'm trying to obtain a district that just contains Y, I'm stuck because I can't fix either X or M. So I can conclude that this is not identified. Okay, a little bit of terminology that Rob will use. So we've now got this idea, I've got a graph, and there are vertices I can fix. And then, so I could then think about graphs, all of the graphs that are obtained, that can be obtained by different, by fixing different subsets of the vertices. So I'll say that a graph G of VW, where these things W are fixed, is reachable from some original graph G star if there's some ordering of the vertices in W such that I can fix each one and get to this graph G of VW. So subgraph is reachable if under some ordering each of the vertices in W may be fixed first in G, then in phi 1 of W, G star, and so on. Okay. So if you were following the way that we did the algorithm, you'll realize that all of the districts that are identified are districts in reachable subgraphs. So essentially, if somebody gave you a list of the things that are districts in reachable subgraphs, if you had that sitting around, then or if you had computed those in advance, if you computed all of those distributions in advance, then any query that somebody came to you with, you would immediately know whether or not it was identified, because if when you expressed the query, when you read step A of Tian's algorithm, there was some district there that was not a district in a reachable subgraph, you would immediately know it was not identifiable. So the sort of the atomic parts that answer every intervention query in the same way that when the DAG's fully observed it's a variable given its parents, I said that we had pieces that look like this, but we can be more specific about this. It's pieces that look like this where D is some district in a reachable graph, in a graph that's reachable starting from the original graph G. And we'll use I of G to denote the intrinsic sets in G. Just to relate this a little bit to previous work, Spitzer, so he came up with a characterization of which were the graphs where things were not identified. This was part of his completeness proof. And he showed that there was a structure, he showed that if there's a structure called a hedge, then the interventional distributions were not identified. And so hedge is like the complement of intrinsic set. So a bidirected connected set is not intrinsic, then there exists a hedge. So the sort of hedge is so Ilya gave a graphical characterization of things that are not identified, and via intrinsic sets, sort of working from the other direction, I was giving a characterization of things that were identified. And this is also the same as the C components that arise from applying Tian's algorithm. Okay, so last thing I'm going to talk about. So all of this was for identification. Tian observed a long time ago. We can also use these algorithms for deriving constraints. And the idea there is fairly simple. It's that, so supposing I give you an observed market from a DAG with latents, then if a vertex is fixable, then I can construct this new distribution. And if the DAG model is true, then this new distribution will obey the Markov property for the new fixed graph, and I can iterate that process. So basically, this gives a way to read off non-parametric constraints that do not correspond to conditional independence in the original distribution, but they do correspond to conditional independence in these distributions obtained by this fixing operation, so by dividing by conditional densities. So for example, here, it's the Verma constraint. Yes, there's a typo here. So ignore the A0, ignore the A0YH. The A0YH should not be here. So suppose that was gone. Cover it up. Okay, so just wish away the A0YH. In that graph, the fixable vertices would be A0, A1, and Y. If I fix A1, then I then get to this graph. I guess I could say, so if the original graph did not have an edge from A0 to Y, then I would then have that A0 is independent of Y from A1. A0 and Y, condition on A1. If this edge were not there, A0 and Y would be deseparated given A1. So we can see that removing this edge gives rise to an independence constraint in this distribution where we fix A1. And it should be noted that in the original graph, if you get rid of this edge, you don't get any independence between A0 and Y, because basically A0, L1, Y forms an inducing path between A0 and Y. So even though if we got rid of this A0, Y edge, there's no way to deseparate A0 and Y, basically because if you don't condition on L1 or A1, then this path is deconnected. If you do condition on A1 or L1, then this path is deconnected. So there's no way to deseparate A0 and Y. So removing the A0 and Y edge from the original DAG with latent variables does not lead to an independence constraint, but it does lead to an independence constraint in this distribution where we obtained by fixing A1. Okay, and here are some references, and I will take rest and hand over to Rob. Questions?
So which of these models are these nested Markov models?
So that's so everything I talked about up to this point was just talking about a DAG with a distribution that was obtained as a margin from a DAG with hidden variables. The nested Markov models will be defined as a set of distributions over observable variables defined by some of these constraints of the type we've seen here again. But Rob is going to go into details of that, so that's going to come up. Other questions?
I was wondering if there are simple ways of understanding the role of the districts by some corollaries or something like it would seem to me that if the whole graph is one district, you cannot identify anything. You always need some information on observed variables outside the district to do something.
Yeah, I think that's right.
Are there any other?
You can identify every causal effect in a graph. That's all one district as long as there are no directed edges.
Yeah.
They'll be all be zero.
Yeah, so not terribly, but basically yes, if I had so that's because all the causal effects are empty. So if everything's just connected by bidirected edges, then if I intervene on any one variable, then I'm just getting Lyson distribution out of something else. Does that make sense? No. I mean, basically, the point is that if everything's connected by bidirected edges, then there's no directed path to any other variable. So whenever you intervene on something, it has no effect on any of the other variables.
Okay, so you already know that there are.
Yes. No, yeah. So I mean, I think Robin was just saying you could have a case where you can identify them. I mean, the thing which is interesting there is that that in that circumstance, essentially intervening on a variable is the same as mathematics. So I mean, it's not having any effect. It's not great news, but you're right. Other questions?
Great. Okay, thanks. So everything that Thomas has done was about doing probabilistic operations on a particular distribution. But if we want to do statistics, then we're not going to be given this distribution. We're going to be given some noisy version of it based on data. So that leaves us with some problems. So we know from what Thomas has said how we would estimate certain interventional distributions given an estimate of our distribution. We just plug in those conditional pieces that we know. So if I wanted to know the causal effect of X on Y, I could use the G formula and just plug in my estimates of each of the conditional pieces that I need, that I've got from the data. But it's not clear that if I use more than one of the versions that would allow me to identify the same quantity, that I'll get the same answer. So in this case, we could use the G formula, which is the obvious thing to do, but I could sort of pretend that I didn't observe L, and then I would be able to use the front door criterion. And I could pretend that I didn't observe M, and instead use the back door criterion. And obviously, if we've got a correct distribution, which is exactly taken from a causal DAG with latent variable, then they'll all give the same answer, because that's what we proved, that these things identify a particular quantity. But if I just have some data that I believe came from that model, then in general they won't give the same answer. So that's slightly irritating. We also might be interested in testing a model like this. So Thomas showed that you could get these sort of strange non-parametric constraints, like the one called the Verma constraint. There'll also be conditional independence tests. So we could test each of those separately, and if one of them didn't look like it was true, then we could reject a model. But that's not very satisfactory, so this is a bit like if I gave you a DAG, and you said to me, well, how do I know that this model is true? I said, well, I've got this list of d-separations, so I could go through each one and test the independence and see whether I want to reject. And that's a fairly dumb thing to do, because for a start, lots of these constraints are redundant, and it could still be the case that even if each individual, apart from multiple testing problem, it could be the case that each of these individual things look more or less okay, but actually overall you have evidence to reject the model. So what we'd like to do is to be able to represent this as a statistical model, to parameterize that model, and then I can just write down a likelihood and do lots of standard inference techniques. So I could find the maximum likelihood estimate for this model within this class, and then because it's within the class, I'll know that all these estimates will be consistent, and that will be the answer that I wanted to give. Or I could use Bayesian inference, or whatever you like. And even better than that, if I can show that the model is smooth, which I'll define later, then we'll get lots of nice properties for free. So one of the things that's important to emphasize is that obviously we know how to deal with DAGs with latent variables. But latent variable models are not very nice things statistically. So they're irregular models, they have an identifiability problem, lack of identifiability problems in general, and they also force you to make assumptions about the latent variables which you might not want to make. So in the case of the Verma graph, which Thomas showed earlier, so here's a version of the Verma graph with fewer edges. If this is the thing that represents the underlying health status which causes my two outcomes to be correlated, that really could be anything. It could be my genes, my environment. I don't want to say that that's a discrete variable with 3 levels, necessarily. So all this suggests that we should try and define a model that we can parameterize, but which doesn't involve explicitly introducing latent variables. So this is what I'm going to try and do. The first 4 sections are about what I've just described, and that's what I'll focus on first. And then if there's some time, I'll talk a little bit about inequality constraints. This is something a little different. Okay, so the approach I'm going to take is to use 2 constraints, 2 properties of the latent variable model, which we know hold, and use them to define a model. So the first thing we know from DAGs is that if I ignore some of the variables at the bottom of my DAG, so I just take what's called an ancestral set, then the distribution over those variables will look as though I deleted the other variables from the graph. So here's an example of this. Suppose I've got this latent variable model. So I observe this factorization, but then summed over U. And now if I ignore 4, grey that out, if I marginalize that, then that's the same as summing over 4. And I notice that because x4 doesn't have any children, it only appears in one of my terms here, one of my factors. So I can push my sum all the way through, and then of course, when it appears in that factor, you just get something that sums to 1, so I can get rid of that term now. And what I have left looks like the factorization of this DAG when I don't have 4 in the first place. And in fact, then I can get rid of the latent as well. So I end up with something which corresponds to the ancestral subgraph of the ADMG from the original graph. So that's property number 1. Property number 2, Thomas showed you already, is that you can factorize things into districts. So remember, if I put back in latent variables corresponding to my bidirected edges, then I can write out the sum. I can split things up into terms which depend upon each district. And then if you look carefully, each factor looks like it comes from a smaller graph defined by intervening on all the other nodes. So this term here looks like it comes from this graph where 3 has the parent 1, 4 has the parent 2, and there's a latent between 3 and 4. So this sort of suggests a recursive structure where I say, well, how do I know I'm in this model? Well, it should mean that there's 3 pieces to my distribution, and each one of those pieces looks like it's from this model, this model, this model, respectively. So that's how we'll proceed. I'm just going to state now that my model of interest is the model that precisely satisfies those 2 properties. So, I'll need to, in general, use a conditional probability distribution, remember, because I may have fixed some things. So I'm going to say a conditional probability distribution recursively factorizes according to some graph if, first of all, whenever I remove a vertex without any children, the margin that's left just corresponds to the graph by removing that vertex. And secondly, that if there's more than one district, then I can factorize the distribution into pieces corresponding to each district and the parents of that district. And then note that I can iterate this process because I might say, well, first factorize it into districts, and then I get a piece which corresponds to a new smaller graph, and then maybe I could apply this again and remove one of the vertices which is now at the bottom of my new graph. So any distribution which satisfies these properties is said to be in the nested Markov model for the graph G. So I apply that to a slightly different version of the Verma graph from the one Thomas had. What can I do for the ancestral property? Well, the only thing that I can't, the only thing that doesn't have any children is 4. So I can marginalize 4, and then I get this graph. And therefore, I can read off from this DAG now that x1 is independent of x3 given x2. So that's one constraint that this model has implied. And then the other thing I can do is to try factorizing it into districts first. So here we've got 3 districts. 2 of them are not very interesting, but the other one made up of 2 and 4 gives us this graph. And now if I apply my first axiom to 2 now, because 2 now doesn't have any children, then I see that in fact 4 does not depend on 1. So this is exactly the same constraint that Thomas gave us before. So you see that you get this independence within this factor, and because P depends on this factor, this is actually gives you a non-trivial constraint for the original distribution. So you might ask why, Thomas mentioned that the advantage of fixing is that you can unify these 2 operations, right? You don't have to separately divide things into districts and take an ancestral set. The reason will become a bit clear a bit later, but I want to convince you that it doesn't make any difference from the point of view of defining a model. So suppose instead I define a model by saying, well, a distribution P is in my model for this graph if whenever I fix V for some fixable vertex V, that the distribution I get is in the model. This is too close to me. Whenever I fix the distribution according to some fixable vertex V, then what's left is in the model for the graph where I fix that vertex. And that's a slightly richer set of operations, so I get to more graphs and I get to more distributions by doing that. But it doesn't actually give me any additional constraints, so the models are still the same. So the reason the recursive factorization version is useful is for coming up with a parametrization and for proving things like whether this is a sensible model to use. Okay, so I want to just briefly convince you that it is the same as fixing. So if I start with, again, another version of the Verma graph, if I wanted to take the graph where I'd intervene on 3, then I can fix 3 and I get this one. That's a valid operation because 3 doesn't have any children within its district, but I can't make that move with my 2 axioms, so I didn't allow that. What I could do instead is split this into 2 districts, and now in this district, in 3's own district, it is childless, So I can marginalize through here. And this sort of gets me to a graph that looks like this. And then I can sort of stick these two things back together again and get the same distribution that we would have got by fixing. And this operation is more or less what we're doing at the last step of the ID algorithm Thomas was describing earlier. So you work out whether you can find all these districts, and then you stick them back together again in order to obtain some other arbitrary conditional distribution, interventional distribution. Okay, so another question you might ask now is, well, there's a typo on the slide, but I could potentially reach the same graph by doing different sequences of fixings. So, or in my case, by different sequences of taking districts and then marginalizing, and taking districts and marginalizing. So how do you know that you get the same distribution each time you do that? And if you don't, that's a pretty big problem. Well, there's a theorem, as yet unpublished, that you can find some of the details in one of the other papers we refer to later, which says that if you can fix two vertices, v1 and v2, in a graph, then it doesn't matter in which order you do it, which is somewhat reassuring. So in other words, if you have a valid fixing sequence, then any other valid fixing sequence which contains exactly the same vertices will lead you to the same graph and the same distribution, provided that you're actually in the model. So this sort of justifies us collapsing our phi notation and just putting a set as a subscript instead of a single vertex. So this means we fix every vertex that's not in R as long as the set R is a reachable set. So remember that means that we can get to it by a valid fixing sequence. Okay, so I'm going to introduce a couple of pieces of notation which will come up a lot. So G square brackets R you've already seen. So I'm only ever going to use this for graphs which you actually can reach by fixing. So Thomas was introducing it as part of the algorithm for graphs which you could get by intervening, but were not actually identifiable.
It was all identifiable.
I think you defined it.
Okay, that was it. That's not right.
Yes, not this, just this. So Thomas allowed you to think about, the ID algorithm requires you to think about graphs that you can't actually identify, potentially, at least in the first step. And I'm going to use QR for the distribution that you get by fixing P. And again, this is unambiguous as long as you're actually in the model. So this is just a sort of review. The GR, remember, is just the CADMG you get by taking the random vertices as being R, the fixed vertices as being any parents of R which aren't already in R, and any edges which are between vertices in R or point from the parents to R. In this case, if I take the district 3, 4, then, if I take 3, 4, and 5, which is not the district, but which is reachable, then I keep 1 and 2 because their parents are 3 and 4, but I delete the edge that goes between them. And the point of what Thomas was showing was that QR is just the do distribution. So it's what you get when you do everything except XR and then look at the distribution of XR. Okay, so it's a slightly more exotic example now. What happens when you recurse these two axioms? So in this example, there's no edge between X and Y, so you might be interested in testing whether or not there was any independence between X and Y. There's no way of de-separating them, but what we can do is, well, we can first of all take this big district here, and when we do that, of course we lose the edge here because it doesn't point into the district. So at the distributional level, I've taken this function of the original distribution, and that's my new distribution, which should obey the Markov property for this graph. Now, what I couldn't do before was to get rid of Z2, but now I can. So I grey it out, and then again I notice that I can get rid of this edge by restricting to this district, which again I couldn't do before. So I do another division, I get another reweighted distribution. Now I can get rid of Z1 because it doesn't have any children. And now you note that there's no arrow between x and y, so this rather weird distribution I have here left that doesn't depend upon x, and it would have done precisely if there had been an arrow there. So that gives you sort of generalized conditional independence that you can determine from your distribution. Okay, so I've given you one formulation of the model, and I've mentioned that there's an equivalent one you can get by fixing, but there are various others. So one of them is to say that for any reachable distribution that should factorize into pieces based on the district without specifying what these pieces actually are. I can also have a global Markov property like one where I say for any reachable graph, then if you get an M separation in that graph, i.e. a D separation, then you'll see an independence in the associated distribution for that graph. And you can also do a similar thing, it's a bit like the ordered local Markov property. So all these things behave pretty similarly to DAGs with cat. And so these results are all the same, just if you assume there is a factorization. Any questions about the model? Okay, so I'm going to move on to try and parameterize this thing now, but first I just need a little sojourn into different ways of factorizing the distribution. So if we take a graph like this, we could define the model by saying that this factorizes into districts, so in this case nothing interesting happens, because there's all one piece here, and then if I marginalize things, then I can see other factorizations and so on. In this particular case, you can see that if I marginalize out 3 and 4, then 1 and 2 are independent. So 1 and 2 are marginally independent of this model. So you might sort of think, well, in a way I could have picked a factorization for the whole thing, which displayed this independence, instead of having to marginalize out things first and then see the factorization. So in some sense, saying that things factorize just into districts isn't the best I can do at any particular point. What you may also note is that in this case it's a bit trivial. Vertices 3 and 4 can never be deseparated from one another. So this piece that I'm taking here is as fine as it's going to get in this graph. So I may as well use this. So this is the best I can do in this particular case. And in general, we're going to find that if you have a graph of one district, then all of the vertices which have no children, I'm going to call the barren vertices, will not be able to be deseparated from one another in that graph. And these sets are actually rather important and special. So I'm going to refer to, given an intrinsic set, so remember an intrinsic set is a district in a reachable graph. So under my axioms it just means I've factorized into districts to get to that piece. If I take all the vertices which have no children, barren vertices, that's called the recursive head, which is associated with this intrinsic set. And everything else in the intrinsic set and the parents is called the tail. So I have head-tail pairs. And these things are all in one-to-one correspondence. So for every intrinsic set, there's a head and a tail, and for every head, there's exactly one intrinsic set, and so on. I guess tails could be shared. So Thomas mentioned that the Markov blanket, very briefly he mentioned the Markov blanket for a vertex which is fixable, which remember is the same as a vertex which is barren within its own district. If you can't have any children within the district. Then the Markov blanket for that is the whole set. And if you remove it, it's the same as marginalizing. So I can just remove the whole head from my intrinsic set, and I don't really lose anything. But now after I've done that, what I'm left with is the intrinsic set without the head, and that may further factorize. So we saw that here. If I remove the head from this graph, which is set 3, 4, then I'm left with 1, 2, and that actually splits into 2 separate districts, so I can factorize it again. So I can iterate this to my heart's content. If I give you a reachable set that has multiple districts, I'm going to define. So I'm going to define a partition of any reachable set into subsets. So that if the reachable set has multiple districts, then the first thing I'll do is split into separate districts and then partition those separately. And if it's only got a single district, then, well, that's an intrinsic set, remember? So I'm just going to take the head off of that district, and then I'll factorize, then I'll partition what's left. And I guess I should say the partition of the empty set is the empty set. Okay, and then there's a theorem which says that I could, instead of using the factorization given in the recursive parametrization, factorization, or on the which Markov property do you describe that as? The factorization property on the other slide that had 3 Markov properties. I could instead do an equivalent one, which is to say for every reachable graph, then the distribution associated with that graph factorizes as a product of the heads in the partition for that set, and each term is just some conditional distribution of the head given the tail. So I think an example is definitely good for now. So here's a graph. It's a single intrinsic set. It's a single district. So it's got a head. The intrinsic set is 3, 4, 5, 6. The head is the barren vertices. That's 5 and 6 in this case. And the tail is everything else. After I remove the head, what's left is this set up here. And this is the intrinsic set 3, 4. It's its own recursive head, and the tail is just 1 and 2. So my partition for 3, 4, 5, 6, following that recursive algorithm, is just 3, 4, and 5, 6. And this tells me, my theorem tells me that this distribution should factorize into these 2 pieces, which in this case is totally trivial. So it's not totally trivial if I first have marginalized 6. So here's another graph now over 5 vertices with a single district. Its intrinsic set 3, 4, 5, and the recursive head is 4, 5. Those are the barren vertices in 3, 4, 5. The tail is everything else. Once I remove 4, 5, I'm left with just the vertex 3. So that must be its own head. And the tail is just 1, because 2 is not apparent as 3. So the partition I get for 3, 4, 5 is this one. And this tells me that the distribution over this graph should factorize in this way. So I end up with a term here where the tail set doesn't depend on 2. And that's a non-trivial constraint, that's because there's no arrow in it. Obviously I could do the same thing by removing 5 instead of 6 and so on. Okay, so lastly, a slightly more non-trivial example. So here, again, there's one district. What's the head? The head is the barren vertices.
4 and 5.
4 and 5, good. So the tail is everything else. So after I've removed 4 and 5, then what happens? How many districts do I have? I've got 2 districts, so I'm going to get 2 different heads. And in fact, one of the districts is 1, 2, and there's no directed edges between them, so the head is everything. And the other one only contains 3. So I get an empty tail for 1 and 2 because they don't have any parents, and the tail for 3 is just 1. So this tells me that this thing should factorize in this way, which again is non-trivial because of the absence of this edge. Okay, so you may be slightly exhausted by the number of different factorizations I've given you now, but I assure you it's worth it. So, to parameterize this, yes.
So is this now a complete characterization of the kind of restrictions or constraints you get?
What do you mean?
Well, you tell me.
Well, they're all the same, so they're all complete characterization of the
well, no, you started with the two axiomatic things, and then with the additional things you get with the heads and tails. So that was something in addition.
I mean, I could deduce any of the constraints from any of the perspectives. So it's not complete in the sense that I could come up with some bizarre piece that I can't get to by fixing, and yet which still factorizes in some non-trivial way. So, complete for what? Is what you would have to ask. So it's richer, but I don't know how you would describe the richest thing that was.
For the subfactorization of the heads was implied by the axioms, so it wasn't a new thing, it's just a consequence of the original.
So they're all the same, right? So I could have deduced that there's an independence here between 2 and 3 given 1 by marginalizing 4 and 5 and then factorizing the districts, and I would get this. So in that sense it's not different.
So in other words, there is not a notion of completeness in the sense that if you have models defined with hidden variables, there's not a way of listing all the
okay, so that's a different question which I will come to later. Yeah. So all these things that I talked about there are the same model, which I claim has an important connection to models with latent variables. But that's a very good question. Okay, so now I want to be able to parameterize this model. I can't really do anything unless I can parameterize it. So what is parameterization? Well, it's sort of map from the model space, i.e. the collection of distributions which I've defined abstractly, to some open set. So therefore I will know the dimension of my model. And we want that map to be bijective and continuous inverse, and ideally we hope this is going to be a twice differentiable map, and that's what we call smooth parameterization. So we're going to assume, for the purposes of this section, that all the variables are binary. It's easy to extend it to finite categorical case. The Gaussian case I think is still open. So the idea is going to be, and the reason we define these axioms in the first place is that we use the axioms directly to try and come up with a parameterization which obeys them. So the game we're going to play now is to proceed inductively to construct our map, and we're going to assume that given a particular graph, all the subgraphs, all the reachable subgraphs have already been parameterized, so we know how to do them. So first of all, if a graph has multiple districts, then it's easy because we can factorize the distribution into the pieces that correspond to those subgraphs, and then we just use the parameterizations for those strictly smaller graphs. And this is nice because all these pieces will be variation independent. So everything's quite easy. So in this example, there are 2 districts. There's 1 and 2, 3, 4. So we would just separate it into a piece for 1 and a piece for 2, 3, 4, given 1. And of course, if you do this for a DAG, then you're done immediately. You just get a piece for each vertex given its parents, and it's fairly easy to parameterize that. But we also want this ancestral property, which is necessarily going to follow from that. So let's say we're interested in this piece now, 2, 3, 4 given 1. We need that if we remove 4, what we have satisfies the Markov property for the graphical 1, 2, and 3. So, what do I mean? Well, I mean if I sum over 4, so I take the piece for when 4 is 1 and the piece when 4 is 0, I get this, and this I know how to deal with by the induction hypothesis. So I'm just going to define the piece with the 1 here to be equal to the thing I know minus the thing with the 0 here. And then I can obviously repeat that process until every vertex which doesn't have any children is set to 0. So if I have one with a 1 in 3 and a 1 in 4, well, I can just do an alternating sum. And these 3 pieces all correspond to ancestral subgraphs, which I claim by induction I can do already. And then I'm just left with this piece here. So we will be tested in a minute. So the procedure is this, remember. First of all, I try to factorize into districts. Then I'm going to get rid of any 1s which correspond to barren vertices in the graphs to the left. Okay, so I'm done apart from this last bit now. Well, so I'm sort of stuck. I'm stuck precisely when I get a head, because that's all the barren vertices, a head that's full of zeros. So if all the elements of the head are 0, then I'm going to apply my finer factorizations, and this is why I bothered to do this. So I'm going to take the distribution of the head given the tail times the piece that corresponds to the graph of everything that's left, which by induction I already know how to do again. So everything that I need is just this piece here. That's the only new thing I need, given that I can do every reachable subgraph. So I'm going to call this probability, the probability of everything in the head being 0 given some instantiation of the tail, beta of the head evaluated at that value of the tail. So I get a collection of parameters for each head, conditional upon each tail. So in general, of course, these will be Qs, because I may have to split them into districts first. So generally the parameters are beta h of xt is QH of 0 given xt. Okay, so now it's over to you. How do we calculate this probability? So the probability to get 1, 0, 1, 1. So what do I do first? So I could do that, but I said it in a different order. So what do I do first always?
Split into districts.
Right, I factorize into districts. So the first thing I'm going to do is write this as Q of Q1, which is actually the same as P of x1 of 1 times Q2, 3, 4 of 2, 3, and 4 given 1. Okay, so now I've got 2 graphs separately which have a single district. So let's deal with this one first. So how will I deal with Q1 of 1? One minus Q1 of 0, and that's my parameter. So that we're done with this piece now. It's 1 minus theta 1. Okay, what about this piece?
Pull off the heads.
Not yet.
Okay.
So what do I have to do first? When we had it originally. Okay, right, yeah, so I want to turn these into zeros, right? So I'm going to do my alternating sum trick. So I'm going to write this as a difference of when x2 is 0, minus when 2 and 3 are 0, minus when 2 and 4 are 0, plus when 2, 3, and 4 are all 0. So now every term in here corresponds to an ancestral subgraph, and everything is 0. So then I do...
Pull off the heads.
I pull off the heads, yes. In the nicest way possible. So this already is a head, this is Q2. 2, 3 is also a head. Sorry, this is 2, 4. So 4 is the head here, because that's just a DAG. And here, 3, 4 is the head. So I end up with something like this. And if I put it all together, then I get something like that. So So that's how I construct my map from models to features. Any questions about that? I'll go through another example a little bit later this time. So this, if you write this down algebraically, what happens is that you find your distribution is of the form that I described if you can write it like this. So first of all, O is the set of all the things that are 0. And then you have an alternating sum over all the supersets of that. So that's a bit like what happened here. This is 2, 2, 3, 2, 4, 2, 3, 4, which are all the supersets of 2. And yeah, it's alternating sum. And then I have the product of my parameters over the heads that correspond to that superset. And I say that the distribution is parameterized according to G if this is true. And I claim actually it doesn't matter whether I assume these parameters are between 0 and 1, because as long as this is non-negative, then that's implied. That's 0. Okay, and remember that if we have a suitable causal interpretation of the model, which I think we've been assuming throughout that we do, then this parameter corresponds to the probability that the head is 0, given that the rest of the intrinsic set is set to this value, is conditioned on this value, and all the parents do this value. So each of the parameters has a causal interpretation in itself, which is quite nice. And the other part, which is interesting, of course, is that actually, so it's obvious from the way I've proved this that if P recursively factorizes, then it's parameterized. Right? Because I constructed it using the fact that it's recursively factorizes. But you can also show that if it's parameterized, then it's recursively factorized. So it's an infinite result. Okay, so just a quick example. Here's the IB model again, change notation slightly. The intrinsic sets for this model are Z, that's a district, XY, that's a district, and X, because I can marginalize Y and X becomes a district. So those are the reachable districts. The heads in each case, well, Z is its own head, X is its own head, and then for X, Y, the barren vertex is Y. And the tails, Z has an empty tail, X has Z as a tail, and Y has both X and Z as a tail. So if you follow that through, the parameterization effectively just corresponds to the probability that Z is equal to 0, X given Z, and Y given X and Z. Sound familiar? So in other words, the model for this graph is saturated. So I think that partly answers Vanessa's question. So this model is bigger than the true model, for a reason we'll see in a second. But we're effectively parameterizing this as though it were the DAG with ordering Z, X, Y. Slightly longer example, which I'll just very, very quickly go through. So if I wanted to calculate this probability for a graph like this, then, well, this is all one district. The head X4 is 0, so I'll pull that out. Now I'm left with the graph where 4 is gone, and this factorizes into 2 districts, 1 for 2 and 1 for 0, 1 and 3. So I repeat, and then if I just consider the graph for the district 0, 1 and 3, then I can marginalize things out, and eventually I get an expression like I had before. So I'll leave you to study that in your own time. So if we're going back to the questions we originally asked here, what we dealt with, well, we know that because we've got a model now, we know that we can pick an element in the model which we think closely represents our data, so i.e. our maximum likelihood estimation, for example, and then these questions will have a consistent answer. So it won't matter how we estimate these effects as long as we do it with a distribution that's in the model exactly. So that's good. We can test all the constraints together. So you can use a likelihood ratio test, as I'll say in a minute, because I can just look at the likelihood of the model, and that's doing everything implicitly at the same time. So I think I suppose it's slightly in the wrong order. As to the question of smoothness, it turns out the answer is yes, and this is the real benefit of not using latent variables. So the model is a curved exponential family, so that has lots of nice properties. It means if we're in the model and we get more and more samples, then we end up with asymptotically quadratic log likelihood, and we have all the usual classical statistical results. And we know the dimension of this model. And we can extend this to the non-binary case. So this means that you can use classical statistical theory. So as I already mentioned, you could use a chi-square test to check your model instead of doing these constraints separately. And you can also use these sort of models as a multinomial response model with continuous covariance. So that's in a paper from UAI from a couple of years ago we used. Okay. So given I have this in the wrong order, I need to come back here. So yeah, we get nice asymptotic for free because we've shown that our model is smooth. And remember, if we use a latent variable model, this would definitely not be true. Okay, lastly, how would you pick a model if you didn't get given the graph in the first place? This is a bit trickier. We saw learning Bayesian networks is hard enough, but this is a much richer class of models. So we had an algorithm where you just replace edges in a greedy search, and that works okay. And you might also ask about how efficient it is to evaluate all these alternating sums, and the answer to that is that that's a paper by Ilya Spitzer, Thomas, and Jamie Robbins, which shows you how to do that in a sensible way. So there's no equivalent of things like the PC algorithm. And this is a bit frustrating, right? Because we define this model by constraints. So you think a constraint-based search might be a good way to go, and it's a project of some interest, but we don't have it yet. So we don't have a systematic way that would allow you to test constraints and end up with a nested model. You can use the FCI algorithm, and that will give you a supermodel of the nested models, because it only considers the conditional independencies. Right? So it ignores these exotic Verma constraints that you get. Okay, and that's the end of my discussion about parametrization. So it's a good point for questions before I go on with some brief notes and inequalities. Yeah.
Is there any advice you mentioned score-based approach? But is it any way how to which scores you can use? Do you have any idea which of the scores you can design?
Well, I mean, we use BIC because we can justify that as being an approximation to the marginal posterior, because we know it's a curved exponential family. We know that if we have enough data, then eventually that will give us the right model. But we haven't done anything more extensive than using AIC and BIC heuristics, which we know are as good as in any other class of sensible models. Okay? Yeah?
So you mentioned the Gaussian case. That is still open. So there's another parametrization for linear Gaussian acyclic directed mixed graphs. I think you call it a latent variable, where you just parameterize the covariance matrix of the disturbance terms. So what is the disadvantage of that type of parametrization compared with the one that you were trying to achieve?
Okay, so the main thing which is you don't immediately know the dimension of the model. So you'll get unidentifiability in cases like the Verma model, which I showed you before. So there's an extra constraint there, which isn't obvious from the parameter count of that ADMG. So in a model like this, for example.
You also lose identifiability. You won't have everywhere identifiability because there can be singularities in the model where you're not. So like the ID model is a you could train parametrics on weak instruments, because if your instrument Z, let's say, is getting very weak, then you're close to being identifiable. So that's supposed to be that.
Yeah, and of course, the point about these thetas is that they're identifiable by the ideal. That's the point. They're all these interventional distributions, so you never have to worry about identification if you use this representation. Any more? Okay, so I just want to briefly return to Vanessa's question. So, I mean, all I did was to take two properties that I know the latent variable model satisfies and define a model as the distributions which satisfy those properties. But of course, there might be other properties that the latent variable model satisfies that we didn't include. So how do we know they aren't? Well, the first answer to that is that you can prove that, at least for the discrete variables, that the latent variable model that you're interested in is of the same dimension as the nested model. So the nested model is bigger than the latent variable model, but it's not bigger in terms of extra dimensions. So that's good. The bad news is that, well, the good news is that that means that if the latent variable model is correct and you're in the interior of it, and then you fit the nested model, then that's as good as if you'd be able to fit the model you cared about, at least asymptotically, because eventually you'll end up with your MLEs in the interior of the model anyway. So that's good news. But the models are not the same. So there are inequality constraints that are satisfied by latent variable models, which we cannot take into account. So this is potentially unsatisfactory, because you might come up with an MLE which is in the nested model that doesn't actually correspond to any causal model that actually exists. So here's a picture of this. So imagine that this is the space of all probability distributions, and this is the space of distributions which can be generated by the causal latent variable model over just the observed variables. And that's our target of interest. So don't worry too much about this O, but the nested model looks like this. So it's of the same dimension, and it contains the model we care about, but in general may be larger than it. So you might end up with an estimate down here. So this was originally shown in this context, at least, by Verma and Pearl. So if you consider this causal model with 4 variables, which is known as instrumental variables, it's very common, then if we only observe z, x, and y, then what we see is something like this. So I'm not going to assume anything about the state space of U, and that's going to be quite important. So we have this factorization, but then U is integrated out. So the nested Markov property, as we already saw, gives the saturated model here, because you just get the parametrization corresponding to the DAG on this ordering. So this theorem back here about completeness tells us that this model is a full dimension, but it's not the saturated model. So you can test for the presence of this edge. So Pearl, in the 1995 paper, derived, which I think is also in UAI, derived these inequalities, which are somewhat exotic looking. So you get things like this, where you take conditional probabilities conditioning on different things and add them together, and they can't be too large. So you can sort of think of that as constraining how correlated Z and Y can be conditional on X. So you could test this inequality, and if it were violated, then you would reject the model. But the nested model wouldn't pick this up. So I think in the interest of time, I probably won't go into the details of how you can derive further inequality constraints, but you're welcome to have a look at that paper of mine from 2012, which is in the references. But it basically turns out that if you have a graph with any vertices which are not joined by an edge, and they don't have a hidden common cause, so in the ADMG sense that really just means not joined by an edge, then there is always some constraint, at least in the discrete case, that you could test. So it may not be an equality constraint, but there'll always be something you can look at. example of this. So this graph is a full dimension, but there are inequality constraints as well. So you can sort of ask questions about equivalence now, and this goes back to something Thomas alluded to earlier. But so I think Vanessa asked, is there a difference between having pairwise latent variables on each of the 3 nodes and having a single latent variable which points to everything? And actually it turns out there is, and that's why you might choose not to use ADMGs, because it won't represent this difference. So if you consider the latent variable model in its entirety, then on 3 nodes there are 8 different models you can have. So there's 5 DAGs shown here, there's the IV model, and there's these 2 more exotic models.
That's not related.
Yes, hence the blank values there. But even on 4 variables, there are specific examples where we just don't know whether they're saturated or not. So we can't describe the equivalence class of models that include inequalities yet. So it's just a much harder problem than even looking at equalities, which is hard enough. So anyone want to tell me whether any of these 3 models represent a saturated model or not? Very interesting to hear. Okay, so I'll skip this, I think. I guess the summary is not really relevant given that I skipped most of the section. So one point of historical interest perhaps is that those of you who've come across any quantum mechanics before may have seen Bell's inequality. You can write down Bell's inequality as being an instance of inequality which arises from a Bayesian network with a latent variable. So that is actually the earliest example of such an inequality. It wasn't thought of as being a Bayesian network at the time. Okay, and there's some references for the inequality section. Any questions?
No more questions left? Okay. Well, thank you, Rob. Thank you, Thomas.